We'll make do. Law of conservation of momentum states that when no net external forces are acting on a system of objects, the total vector momentum of the system remains constant. In other words, in English, momentum is conserved. In fact, I like to say every one of these questions can be started with PI is equal to PF. PI standing for initial momentum. PF is final momentum. So the initial momentum is equal to the final momentum. It's a good sort of starting point that allows you to sort of figure out, okay, what's the initial momentum, what's the final, and make it all sort of together. Yeah, the initial momentum is equal to the final momentum. The total vector momentum of the system remains constant. Equals, before, after. They're the same. Well, there could be there's no delta P. There's no net delta P, that's correct. Of the system. In English, the momentum before is equal to the momentum after, provided there are not other forces acting. Okay, so here is the classic situation. You've got a boy and a man on roller skates, rollerblades, I guess you could say now. Right? And they're just stationary. And man decides to give boy a push in the back. Boy goes forward, man goes backward. What's the total momentum before? 0. Right? The total momentum before, this is PI is equal to 0, which means that the final momentum is also 0. Mr. Bennett, the final momentum can't be 0, they're both moving. The final momentum of the system is 0. So after the explosion, I guess you could say, this is actually an explosion, because they were together and then they explode apart. Right? So after PB, which is?
We're going to get a chance to draw those.
Do you want to draw momentum, boy?
Right there. Do it.
It's all right.
Oh. Whoa.
Momentum, boy. You like that?
I think you be the boy.
The only question is momentum man just a grown-up momentum boy, or is momentum man like?
It's like Mermaid Man and Barnacle Boy.
Yeah?
Yeah.
There. Yeah.
Barnacle is actually like old.
You'd love to see me in that trend, actually.
Probably.
All right, I think maybe we'll stop the conversation there. All right, so going back to PV momentum boy. So that's going to be mass boy times velocity boy. And the mass of the boy is 40. And the velocity of the boy is minus 0.5. Why minus? Because he's moving left.
But wouldn't you say that he's moving forward and the other guy would be minus, so he's moving
Does it matter? Good point. It doesn't really matter. If I define this direction as negative and that direction is positive, then
But
yeah.
how would we know that it was negative or positive?
You can define it like that. But if you define this as negative, then this one has to be positive, right?
Could we not define that as negative? Could we just say it's going forward? Yeah.
No, because then you're going to have 40 times a half, you're going to have 20.
Yeah.
And 80 times a quarter, you're going to have 20, and 20 is 40. And the momentum final must be 0.
Well, if you can do whatever I want, then I can do whatever I want. There's a rule now. No,
Yes.
Always for momentum is always going left is negative and right
Yeah,
is positive.
yeah.
No, the only place you can switch it around.
You can switch it around if you wish. Yeah. Like that's what Steve asked. He said, well, this guy's going forward. Can we say that's positive? Sure, but then you have to say this one's negative.
That's what I said. I said, can we have the front one positive?
Sure.
And you said no.
No, I didn't.
Can't you?
No, Hannah.
Oh my gosh, do not keep a child. I am.
I'm going to say that left is negative and right is positive. 40 times negative 0.5 is minus 20. Momentum man, velocity, it's mass man, velocity man. It's like a Cheech and Chong movie. 80 times 0.25, which is positive 20. We'll put positive in there to emphasize that. Total momentum?
Whoa.
If you can keep that in mind, that the initial is equal to the final, always, this time it's at rest, what if they were already moving both of them forward? Like, let's say they were moving forward at, eh? What, exactly. Okay? So minus 20 plus 20, the final is equal to the initial, whether it's 0, 50, a million, whatever. Doesn't matter what it is. Okay? This is an example of an explosion. Because they were together and now they explode. I think. There are two types of collisions. One is called inelastic. Is that what's coming up next on yours?
Yeah.
Excellent. So suppose we have two carts of equal mass traveling at the same speed, but traveling toward one another. If there is no rebound effect, no rebound, because they hook together, maybe there's Velcro or something. This is an example of inelastic collision in one dimension. Inelastic means no bounce. There is no bounce. If this is mass 1 and this is mass 2, what is the mass of the combined system? Well, it's mass 1 plus mass 2, right? It's the total. Like if this is 200, well, it would be kilograms, 200 grams, then this would be 400 grams. But what would happen? If they were equal velocities, what would happen here? Would they move anywhere? Just stay right there, right? The total momentum before must be equal to the total momentum after. There's momentum boy and momentum man. You've seen them already. Kind of looks like Garrett a little bit, I think. Garrett Fletcher? Yeah? He drew it for me. Momentum of cart A, right here. Do you have it labeled or no?
Yeah.
Excellent. Momentum of cart A is MAVA. Here's that subscript thing that I told you about at the start. Momentum of cart B is MBVB. But the velocity of A is actually negative velocity B. Right? Because like if this one is 5, this one is minus 5. Or the other way around if you want. Right? So therefore MAVA is equal to minus MBVB. Or in other words, the total momentum before again is 0. Even though they are both moving, it's the opposite of momentum man and momentum boy here. Right? Opposite idea. The total momentum before is equal to 0. So this is true if this is an isolated system. Both carts had kinetic energy before the collision, but there is none after. Kinetic energy here. Kinetic energy there. Is kinetic energy a vector? It's not. So the momentum must be conserved, but this energy, if there's like say 100 joules of kinetic energy there and 100 joules of kinetic energy there, there has to be 200 joules of energy after. But where does it go? Because it has to go somewhere. There must exist 200 joules of energy somewhere. But they're not moving. What is it? Heat. Suppose I took two really smooth stainless steel spheres, big balls, slammed them together with a piece of paper in between. What do you think will happen, John?
It's gonna light on fire.
You think so? We should test it. Okay, so that was pretty cool.
All right, you really missed out.
I'm glad we had the fire extinguisher for that. I'll have to get Mr. Federchuk to recharge that fire extinguisher because we needed to completely use it to douse that fire. Is your hair okay, Zach?
I don't know.
Yeah? Those eyebrows will grow back.
My brother went to with the His eyebrows gone.
Okay, let's do some more problems. If one car had a greater mass and the velocities remained the same, will the outcome be different? And the answer is yes.
Why don't they last together?
They will latch together. But because there is, before, the total momentum was 0, right? They were both moving at the same speed. They were both moving, had the same mass. So the total momentum before was 0. Now, velocities remain the same, but B is twice as big. So what's going to happen to the two of them after? They're going to move which way?
Whichever way has more momentum.
Exactly, which in this case would be to the left, or negative. To the left, right? I actually have two cards here. If I have time, I'll show it to you. So suppose mass A is 100, mass B is 200, so twice as big. The velocity of A is +2, the velocity of B is -2. Here's how you would do it. Now, I don't know what, do you guys need to fill anything in here? No, you don't. Awesome. Okay. So what's the total momentum before? PI is MAVA plus MBVB. Mass A, velocity A, 100. Does it have to be in kilograms?
Yes.
It probably should be. Oh, but this says 100 grams, right? So I guess that should really be a decimal there. And that should be a decimal there, that should be a decimal there, right? So it's 100.1 times 2, or 0.200. 200 times -2, minus 0.4. And so you get a total initial momentum of minus 0.2 kilogram meters per second. So there is not an initial momentum of 0. There is an initial momentum that is to the left, which means after the collision, there's going to be 0.2 kilogram meters per second of momentum to the left. The two carts together are going to keep sliding to the left. PI is equal to PF, or 0.2 kilogram meters per second. How fast are those two objects going together, do you think? What's the mass of the combined system after? Mass A plus B is going to be 0.3 kilograms, right? 100 plus 200 grams. Going to have to add them together. That's what we do here. So PF is equal to MA plus B, VA plus B. See those crazy subscripts? Where mass of A plus B is equal to mass A plus mass B, 100 plus 200, 0.3 kilograms. So the final momentum must be minus 0.2, I guess, not 200. The final momentum must be minus 0.2. Why? Because the initial was minus 0.2. Is equal to 300 times, what's VA plus B? What does that stand for? VA plus B. What does that stand for?
Velocity of A.
Velocity of the combined two carts, right? So it's going to be minus 200. We're going to divide by 300. The combined two carts are going to be moving to the left at minus 0.67.
When did they turn from 0.3 and 0.2 to 210?
That's just still.
They were in grams.
You did.
Yeah, they were all in grams. Yep. Okay, so before, let's just go back here. One was moving to the right at 2 meters per second. The other one was moving to the left at -2. When they combine together because of their mass, this guy had more velocity, so they overall end up going to the left at minus 0.67. Does that make sense? I'm looking for some feedback here, you guys. I see a lot of people just sort of, you know what I'm seeing? One of the things that we can do, the I and the F are handy, but it becomes another subscript, right? Like I could say PIPF, I could say MAVAI, MBVBI, but another way to show before and after is this prime notation. And all it is just an apostrophe. If you put an apostrophe after the V, it indicates that it's after some event has happened. Okay? So it's just another way. I'm throwing it in now because you might end up seeing it in the future. It just means after the fact or something like that. Okay, Kelana? Yeah. So let's fill in what we know. MAVA, mass of A, 4. Velocity of A, 6. Mass of B, 2. Velocity of B is 0 though to begin with, right? Which means, how much momentum do I have at the start? 4 times 6 is 24 plus 0 24 kilogram meters per second of momentum before. How much do I have after? 4. Oh, now hang on here. I think I made a mistake. This is a combined mass, right? Yeah, okay. So this is wrong over here, isn't it? What should this read? Should read mass of A plus B together times velocity A plus B together. Right? I've got the mass, the total mass of A plus B together. Mass of A plus B. Velocity A plus B. So what is the mass of A plus B? 4 plus 2, right? Can I just write 6? You know what?
Yeah.
For the sake of notes and examples, I'm going to write 4 plus 2 together. For Ryan at home, yes. So what is the velocity of A plus B after? 24 divided by 6 or meters per second. And does the direction matter here? Is it going, this is saying, telling me that it's positive. Is this thing going to move positive? This is a great big guy. He's moving at 6 meters per second. The little guy is 0. He's at rest. Is this thing going to continue moving to the right? Absolutely. Is it going to look like this? Fire. Would there be heat generated here?
Yeah.
Probably some, but not near as much as together like this, right? There wouldn't be that massive explosion like we just saw.
So do we get to do an explosion in this game?
Actually, you know what I'd like to do is, you know that when I was a kid we had cap guns, you know? That always scares me. If you can convince Migalski to do it, you go ahead, but I ain't doing it.
Do what?
That, like that you're talking about, is known as an elastic collision. When they do not stick together, they rebound off each other without a loss of kinetic energy. So when Steve goes running into someone a little smaller with the exercise ball, that smaller person's going to go flying, right? Is there a loss of kinetic energy in the real world? Yes, there is. Perfect elastic collisions occur between atomic and subatomic particles only. In the lab, pool table balls or those stainless steel balls like that I had will do just nicely. So suppose the same two carts are involved in an elastic collision. This time cart A is moving at 2 meters per second, cart B is at rest. Find the speed of cart B after the collision. Do you want me to do this one for you? Or do you want to try it?
Let's do this one.
Want to do this one? Okay. Okay. Well, let's change those masses to kilograms, right? 0.1 kilos, 0.2 kilos.
Where is this even? I don't even have.
Yeah, you do. Bottom right-hand side of,
I know, but it just doesn't show a lot of it.
yeah. I got to get this slideshow more in sync with my version. I like to start with PI is equal to PF. It helps frame my thinking. I keep everything that's initial on the left, I keep whatever's final on the right, and it's just a good way of sort of organizing my solution. Zach.
How did you like my solution for Crazy Eddie?
I don't remember.
Oh, it was all over.
Yeah?
You didn't get an answer, I just left.
Just kept numbers everywhere.
Just left it on the paper.
Okay, so PI is equal to MAVA. I also has MBVB in there. MAVA after collision or prime. MBVB prime after collision. Now this time they are elastic, so we do not combine the masses. Okay, so you have to watch the question to see, are they stuck together or are they not stuck together? Fill in what you know. MA is 0.1. Velocity A, 2. Mass of B, 0.2. Velocity B, 0 at rest. Mass of A, 0.1. I think we are, aren't
We need the velocity of A.
we? You sure do, don't you?
Moving at 2
Let's say it's 1.
The car is moving at 2
Or do you think it would stop in its tracks?
Well, let's say it's 0. Let's say all the momentum is transferred. So let's say that after VA is 0. Let's do that. Let's see what happens. Hi, Mr. Dart.
Hey, Mr.
I'm almost done here. Can you give me about 30 seconds?
Absolutely.
Okay. So MAVA prime, let's make that 0. Good suggestion, Steve. Mass of B is 0.2. Whoops, I got 2 decimal points.
So what did you put for?
We decided that we're going to make the velocity of A after is 0. We're going to transfer all the momentum.
It's flat as opposed to positive.
Do you see how these stuff, like, do you see how it can get messy?
Yeah.
Can you look down the road and realize when it's two-dimensional what it's going to look like? And everything's broken into vectors?
No, let's not do that.
Gosh, that sounds like fun.
Oh.
Oh, you guys are just saying that.
That was I wanted to react.
Well, you're probably trying that reverse psychology on me, where you say you don't want to do it, but you really want me to. Okay, okay. 0.2 VB prime, right? The zeros disappear. 0.2 VB prime. Hey, this is going to be easy. It's a whole lot of writing to get to
1.
1.
So mad.
It is kind of magical. 1 meter per second. So the little guy was moving at 2 before. The big guy who was like twice as big is now moving half as fast. Does that make sense? Right? So if you were doing that lab that we're not going to do and the small person ran into the big person, they would move away like at a half speed, right? Which is what you would expect. I think is there one more to try?
Yeah. No.
Well, there's an example on the back there, right? Okay. You've got this is a different page.
That's what I want.
So you've got 1 at rest, 1 both moving in the same direction, 1 opposite directions. Try that first one right now. I will say that I'll start you off. I'll start you off with
Well, that formula.
PI equals PF. They all start the same. They all start the same. You just have to figure out what makes up the initial momentum and what makes up the final momentum. It says 1 ball, 2 ball. Could we just call them A and B? Like, it doesn't say that in the question, but can we just do that? Why not? Right? We've got A colliding with, they're opposite directions, right? So A is going this way, B is going that way. Okay, does that help?
That's the third question.
You're so picky, Quinn. Like, really, what does it matter which question I do? Thanks, Quinn. Okay, so we got A and B. One's at rest. When one's at rest, it's easy. PI is equal to PF. MAVA plus MBVB is equal to MAVA prime. In fact, this line is almost exactly the same every time, right? If you call them A and B. It's really just a matter of plugging in the numbers that work for it. 4 kilogram ball moving at 4 meters per second east. So that's going to be, east is positive, 4 times 4. Mass of B is 2, but it's at rest, so it's 0. Now you can keep going if you want. I, for some reason, kind of like doing all the left side first. You don't have to. I don't know why I like doing that. It's kind of that before after thing. VA prime, if the final velocity of the 4 kilogram ball is 2 east, so that's going to be 4 times 2. Mass of the second one is 2. VB prime.
Why is it 2?
This one?
No, why is the mass 2? Yeah.
The masses here are going to be the same here, right?
Oh, definitely.
I think it's handy, actually.
No, I got it wrong then.
I guess, really, do this, right? Do the positive and negatives matter in these situations? Yes, get them right. They got to be right. 8 divided by 2, 4 meters per second. Hard?
No.
Not really. Just, you got to get used to doing the setup, right? I really encourage you to sort of set them up like this. Take the time to do the setup. It helps. Okay? I'm going to stop because you've been very patient with me. There are 2 more sample ones. What I'll do tomorrow is I will do this one, and then you've got 2 more in the back that I'm going to have to find and put in there. I'll do those 4, and then I'll give you some time to work. And we're going to briefly touch on 2D on Monday.
Can we